Hello, this video is to help students understand where the Bernoulli equation comes from, which is essentially the equation of how we handle conservation of energy in fluids. So what I hope is familiar to you is that conservation of energy is a useful strategy for dealing with objects that move from one location to another. So this is a problem you might have seen in the first year physics class. I have a roller coaster. It's got a speed. It's changing its height. So it's moving from one height to another. And conservation of energy is a great strategy for a problem like that. So what I teach students to do is I have them write energy original and energy equals energy final. In other words, conservation of energy. Just that means that in the two locations, our total energy is not going to change. The next step I have them do is I have them identify what types of energy they have in each location. So at the bottom, our roller coaster car is moving fast. It has kinetic energy. At the top, it's gained potential energy because it's gotten high. And it's probably still moving. So I have them as EF list the sum of those two types of energy. From that point forward, they can just plug equations in. We know the equation for kinetic energy, the equation for potential energy. And typically there will only be one. Can solve for what the final velocity is at the other location. There are other energy types besides kinetic and potential, of course. In this problem, I'm dribbling a basketball and giving it a little push as I get started. So it's going from up high to down low, so potential energy is turning into kinetic energy. And that little push, we can call it work. So we can add a work term in. And then I can plug the equation F delta X or FD, however you want to call it. And I can incorporate work in that way. So EO equals EF is really, really powerful. And we're going to now use it for fluids. So let's look at the ugliest possible case we can see for liquids moving from one place to another. It will derive a big, scary formula that we can use in almost every case. But in most cases, we won't need to use every term. So imagine I've got a pipe full of water. This water is flowing in this direction. So notice that like the diameter of the pipe has changed. The height of the pipe has changed. It's pretty complicated. But since we know water is incompressible, let's say in a given time period, this volume of water is lost from up here. That means that later, an equal volume of water is going to be gained down here. We also know that there's water pressure, which is going to put a certain force, let's call it F1, on the whole column of water here. This water behind is going to be pushing everything that way. And there's water up here too. This water is getting pressed into it. So it's getting pushed backwards. We'll call that F2. So let's do an EO equals EF equation for this bit of water as it's moved in that direction. What do we have at the beginning? Well, presumably we have some potential energy. We have some kinetic energy. And at the end, we also have potential and kinetic, but a different amount of each. The water is moving this way. So F1 is going to be doing positive work. It's adding energy to the system. But F2 is fighting that push. So it's going to be doing negative work. So that's our overall equation for the system. Sorry, lost that for a second. And what I want to do now is basically just plug in values you already know. And we'll try to see what this looks like for a fluid situation. So I'll start with potential energy, MGH, kinetic energy, work is going to be F x1, so this we'll call x1, minus, and that's F1, minus F2, and we'll call how far it moves x2. And that's going to be equal to mgh2 plus 1/2 v2 squared. So already our equation's gotten pretty complex, but hopefully you can see how this became that and that became that. Just going to make a couple substitutions to make this a little more fluidy. So I'm going to sub in from mass. So this is going to be P V G H1. That's going to be 1/2 PV V squared. Oops, that's a 1 right there. Plus F1 x1 minus F2 x2. Rho V G H2 plus 1/2 rho V V squared. What else could I do to make this fluid? Well, these forces are going to be causing pressure on the fluid. And since we know pressure is defined as force divided by area, force is going to be PA. So I can plug that in. So my equation then becomes rho VGH1 plus 1/2 rho V V1 squared plus PA x1 minus P2 A x2, so it's A1 and A2, equals all the same stuff. So again, looking complicated, but hopefully you're seeing that all I did was sub in PA for graphs. And one last little bit of trickery. What's A times X? Well, if that's A and that's X, what we've just defined is a volume. So this becomes P1V, the volume, minus P2V, and the one thing that is constant in all these terms is volume, because water is incompressible. So I can divide out V. What I'm left with is rho GH1 plus 1/2 rho V1 squared plus P1. While I'm at it, I'm just going to move P2 to the other side. Is rho V excuse me, rho GH2 plus 1/2 rho V2 squared plus P2. And this is called Bernoulli's equation. It's a statement of conservation of energy. The way it's written on your AP equation sheet is rho GH plus 1/2 rho V squared plus P equals constant. Basically saying the same thing as the roller coaster equation. Potential and kinetic energies added together at any given time. The sum of them. We've just got a little bit of extra in here for the work, which in this case, it's pressure. So we will use this equation extensively whenever we are looking at fluids that are moving. Typically, sigma F equals ma. Statics is best when we say fluid that's not moving, but this is great when fluid moves from one place to another. Just so you know, this is called the Bernoulli equation. Since there's a lot of terms here, and that's a lot of measurements to take, in a lab, we're typically going to try to set this up where most of the terms on one side are either identical or equal to the terms on the other. So typically this will simplify to a much easier situation.